PEM electrolyzer stacks. Is there a right way and a wrong way to run them? Or is the wrong way the right way? These technical instruments are so important that we need to talk about them. And we've brought an expert on that on Hyfindr Tech Talks today. I'm very excited to have him on the show. He's been here before and he has built big systems and now he's all focusing on stacks. Welcome, Max Ellerich.
Hi, Stephen. Nice being here.
Great to have you, Max.
Thanks.
So can you start right out by telling us what is an electrolyzer stack and where can we find it?
Yes, sure. I mean, when you're having like a big system, a containerized system which produces hydrogen,
Yes.
the core, like the heart of it, where the magic happens,
Yes.
is actually the electrolyzer stack.
All right.
So every electrolyzer, big system, has an electrolyzer stack included.
Yes.
And I guess this is what we're talking about today.
Yes, exactly. Yeah, and I'm very happy to mention that Max has made another video with us on this show here where you can learn all about the different components that make up an electrolyzer system. So you can watch that one to find that out. And I'd just like to loop in one more thing, and this is also, I think, why it's important that we talk about today, because we had the CEO of Aqua Power from the NEOM project, Saudi Arabia, talking about producing hydrogen and how, at the end of the day, when you have these huge solar fields, how much hydrogen you make depends on your electrolyzer. And I think the heart of that is the electrolyzer stack. So that's why it's so important to look at the efficiency of that one.
Yes, 100%. I mean, it's all about efficiency. So often people are talking about the capex of such system, right?
Yes.
But I mean, down the road, it's all about the Opex at the end, because
Yes.
this will just be much bigger. And this all boils down to efficiency of an electrolyzer, which again really is about the efficiency of the electrolyzer stack, because I guess like 92-93% of the electrolyzer's energy consumption is within the stack.
Is within the stack.
So this is what you got to deal about.
Okay, cool. So we'll be doing some math later on, so stay tuned for that. But maybe, Max, if you could start by telling us how does electrolyzer stack actually work and how the innards of all of that.
Yes, of course. So, I mean, generally a stack, I mean, you see a picture I brought here.
Yes.
I didn't bring the stack because it's like 500 kilograms.
All right, okay.
But it's like, I would say this one here is like this size,
Yes,
roughly, like that.
Okay.
And I mean, within the stack, you have like many cells, yeah?
These are them here, yeah.
Exactly, so these cells, like cell by cell by cell, it's
Yes.
all stacked, right? This is why
On
it's
top
called
of
a stack.
Yeah, on top of each other.
And this is then pressed together. So you
Yeah.
see the springs here, the green springs,
Yes.
this is all compressed.
Okay.
And then within each cell, you feed the water, and we can look into it a little bit here.
Yeah.
Let me just show.
Yeah, there
Yeah.
you go. Mhm.
So just another idea to
Yeah.
get an idea,
Yeah.
and also to get an idea of the size of these stacks we are
Okay, so
talking
these are
about here.
textural humans, and then you can see the.
Exactly. Like you see like 4 stacks here in a row,
Right.
so you get an idea on how big it is.
Okay.
And actually, you already raised the question: is there a right way or a wrong way? So there are definitely different ways of how to operate a PEM stack.
Okay.
What we are talking about, and I just wanted to highlight the difference.
Yes.
Right. So I mean, in each of these cells, that you have there, in every cell, the same thing is happening more or less. So you're feeding water to the cell,
Yes.
and this is what we're showing here. So
Okay.
this is like
So this is like a cross section of one cell.
exactly.
Exactly. So just to play, we are looking at one of these.
Exactly.
One of these. Okay.
So we're having one of these, and then we have them turned here,
Turn
and
to the
this
side. Yeah.
exactly,
Okay, cool.
exactly.
Alright, okay.
And this then happens over 100 times in parallel.
Tack, 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 over.
Exactly. So and what's happening with the cells actually is for a classical PEM stack, what you have like water feed. This is the anode side, so you feed water to the cell,
Yes.
push it into the stack, and then there is like a voltage applied to the overall stack,
Yeah.
right?
Okay. Electricity. Yeah.
Exactly. So, and this electricity then distributes about all the different cells,
Yes.
right? So, when each cell has like a voltage and has water running through it.
Yeah.
And while the water is running through the anode and it hits the surface of this membrane, this gray thing here in the middle is the membrane,
Yep.
the water will break into hydrogen and oxygen,
All right.
right? So the water, it will break, and then the hydrogen is being pulled through the membrane to the other side. Or it's not the hydrogen, it's a proton. It's the core of the nucleus of the hydrogen. This is why it's called PEM, proton exchange membrane.
Yeah.
So the protons are going through the membrane. So the protons will go here to the other side, but the membrane will not be open to oxygen.
Right.
So the oxygen will kind of stay here on this side,
okay.
right? So the protons go through it. And by the way, when there's a proton going through it, also water will go through it. It's called water drag.
Right.
So the membrane is open to water in some kind.
Drags some water along there.
Exactly.
Okay.
Actually, it's way more water than protons going
really?
through the membrane. Yeah, by weight, it's way more water.
Yeah.
But that means on the other side, you have like hydrogen, because the proton recombines on the other side, on the cathode, back to hydrogen. It gets an electron and then 2 protons, and it's H2 that you're generating then on the other side. And you have the water, and that means on the other side you have like water and hydrogen going out. And here on this side, I mean, you're pushing the water more and more.
This is pressurized water?
Exactly, yes, yes. It's just they have a pump and this is just flowing.
What kind of pressures are we talking?
It depends on the manufacturer. It ranges from 1 bar, it can be atmospheric. Others go up to 30 bar even on this side. Usually on the other side you have pressures of around 30 bar mostly. So because the pressure will build up over the membrane. And then you have the oxygen, and the water is flushing out the oxygen. Right? You have a continuous water flow here. Oxygen is being not created, but water reacts to oxygen, right? And then the oxygen is being flushed out, and you have like sparkling water, but not with CO2, but water and oxygen here, and water and hydrogen coming out on the other side.
So that and the water and hydrogen coming out on this side, and then you would need to dry that hydrogen, basically, or rid the water of the hydrogen to get the actual hydrogen you use.
Exactly. Then you purify the hydrogen and so on. I think this is we talked about this exactly in this one video.
What's in the box. In the
exactly. Exactly. That's what's all happening in the container. So and this is what's happening in the heart of it, I'd say.
Okay.
So that's the classical way of how to do it.
Right.
So Hystar has a different way of how to do it. And actually, Hystar is feeding the water from the wrong side. Or maybe the right side, so we got to discuss that question, right?
Yes, exactly, okay.
So we are practically feeding not the water from the side where you actually need it. I mean, this is a cell like this one, yeah? It's just the same. But we feed the water from the other side.
So from the cathode.
Exactly.
The others, well, let's say the usual way is to feed it from the anode. And then you go and feed it in from the cathode.
Exactly. So this is what's happening. And then the water, I mean, I said that the membrane is open to water. So the water will soak through the membrane to the other side, also in our case here. So the water that you feed here goes through the membrane. And then the same reaction happens as happened here. So when the water reaches the anode, the water will split into hydrogen and oxygen. And then the hydrogen will go back again. Right, so then the same thing actually happens as happened here. So you have here the creation, hydrogen, oxygen, and hydrogen then going back through the membrane again.
And you have the same mix of water and hydrogen coming out.
Exactly. So this more or less, if you compare these two sides, it's more or less the same.
Yeah, and it's okay. This side you have water and oxygen, this is okay. All right.
Exactly. So on this other side, so on the anode, you have oxygen left, right? Because the oxygen still cannot pass through the membrane. Exactly. But here we don't have water to flush it out. So Hystar uses air. So we blow air, we compress air through it, and the air is then carrying out the oxygen.
Okay, what kind of pressures are we talking in this case?
So the air is more or less atmospheric.
Okay.
It's just in some pressure in order to enable the flow there.
Blow, kind of,
exactly. And on this side here, we are talking about 5 bar. Around 5 bar at the end of the stack that we are creating with the hydrogen.
Okay. So you just, why do you do this? Why do you just, I mean, you just want to do things differently.
Maybe this was initially one of the reasons, I don't know. No. So this comes with some advantages. And this is what I just would like to highlight here. So, I mean, when we're doing it like this, there's something I didn't tell you when I was showing you this one here. Actually, what I didn't tell you is that you have a continuous hydrogen crossover. This is hydrogen, which have been created here, went through the membrane, and then is going back through the membrane again. This always happens. It's a hydrogen crossover when the hydrogen goes from the cathode side to the anode side through the membrane. It's being pressed through it. So you can see it here with these arrows. This also happens in our case, but actually it's a problem. It's not a problem because you're losing hydrogen. We are talking about maybe 0.1% or something. It's not a lot.
Amounts,
exactly. It's really, really, really small. But the problem is that if you have hydrogen, even small amounts, mixing with oxygen, you are having like an explosive gas. So especially when the hydrogen and oxygen reaches a distant limit, right? Then you will have an explosive gas, which is a problem from a hazard perspective for your system. So the point is that this comes with some limits. So for Hystar, actually, this is not a problem because Hystar can control the airflow. I mean, by having this other principle of how to operate a stack, then we continuously measure the hydrogen in air or the hydrogen in oxygen here, up here. And when we see, hey, this reaches like a certain limit, we just blow more air. So the blow of air is controlled by the amount of hydrogen diluted in air and oxygen.
Okay. So the let me say the challenging thing is the combination of these two.
Exactly, of these two.
Of these two. Okay. So that means by pushing in more air, you can actually make it more diluted.
Exactly.
Okay.
And this you can't do here because by pushing more water,
Yeah.
you don't have more oxygen where you dilute it in because it's only diluted in gas, right? So while I can just put more air here, I dilute it more.
Because here the oxygen is the same oxygen that gets created when the hydrogen gets created. So
exactly.
You have your that's a stoichiometric ratio.
Yes, exactly.
Is that one?
Exactly.
Yeah. Whereas here you can push in extra just from that. Okay. Then
exactly. So, and this is exactly the point. So here's always the ratio is more or less the same, or the ratio is more or less given, right? And this gives you some limits. Here you don't have this issue.
Okay.
So what the point behind this? I mean, every electrolyzer system is safe if it's operated in the right way, and this is not the thing. But you have to, in a classical system, you have to prevent for too much hydrogen to cross over this membrane. So how you can do it is how you make a bigger membrane.
Okay.
So the bigger the membrane, the less hydrogen can get through.
Thicker.
Yes.
Okay.
Yeah. Not bigger. Yeah. Thicker is more right. Sure. So and therefore you limit this hydrogen crossover that you have. Okay. The problem is, if you have a thicker membrane, you have a lower efficiency on your system. Okay. I will just come to this in a second. Yes. So therefore, Hystar can just use way thinner membranes. Yes. Yeah, because we can control this hydrogen, oxygen, or hydrogen and air. Yeah. And therefore have the chance to make the membranes thinner and therefore increase the efficiency of the systems.
Okay. So thinner membranes allowed because more air can be blown. Then
exactly.
Okay, so that's this. Okay,
and this is very interesting because I mean, at the end, the components, the materials that are used here and in a classical system are more or less the same. Yeah, it's more or less the same membranes, just thinner, right? It's the same catalyst, and it's not the same, but you know what I mean. It's not too special about this, but it's really special about that you can just make the membrane thinner, and therefore.
And how does this thinner membrane make the system more efficient?
This is actually I have like a slide on that one.
Yes, okay.
Where we can just do a little bit theory behind it. Okay. I promise I don't go too deep, but just for general understanding.
Okay, let's fasten the seatbelt and go for this.
Let's see. So what I brought here is a diagram which shows the hydrogen production. Yes. So I mean, going here means I produce more hydrogen.
In kilo, yeah.
Yes, exactly, in kilograms. And this is the relative energy consumption, or also the relative energy losses, more or less, that I need to produce hydrogen. Yes. In an ideal world, if I produce 1 kilogram hydrogen per hour or 100 kilogram hydrogen per hour, I would always use the same amount of energy per kilogram hydrogen. Yes. Of course, it would be 100 times more, but then I would have 100 times more hydrogen. So relatively, this is like stable, the reversible process. Yes. Yeah, okay. In an ideal world.
In an ideal, okay.
But we are not living in an ideal world. So there are different contributions to losses in a PEM electrolyzer stack. Yes. Okay. So I just brought some here to give a general idea. So you first of all have electric losses. Here for your electrons, they have to go through some cable or through the whole system. So you have electric losses, like you would have a loss in a cable. Absolutely. Yeah, where you have some electricity through. You have mass transport losses in a stack, which practically means if your water is reacting at the membrane, then the hydrogen and the oxygen is blocking new water from getting there.
Okay.
Right?
Taking
so,
up space,
because first the bubbles have to go away, then new water can come. So this is what you have there. You have activation losses, which you have to overcome in order to more or less trigger this reaction, which is happening with the water. Okay. So, and you see all these losses are in a different amount. I mean, this is a qualitative idea that I will give here. It's not quantitative, but it shows that depending on the amount of flow, some losses are getting bigger, some are getting smaller, and so on.
Understood.
You have proton ohmic losses. And the proton ohmic losses are the losses when you have the membrane and your proton goes to the membrane, then it also creates a loss.
It's like a resistor.
Yes, it's actually the same as these electric ohmic losses, which is why it's called the same, most likely, I guess. Yeah, okay. But this is with the proton, which goes through the membrane, creates a loss. Okay. And I mean, with a cable, if you have a loss through a cable and you make it shorter, your losses are less, exactly. Right? And this is the same idea. When you add up all the losses, you have the total relative energy consumption of your electrolyzer.
Understood.
And what it practically, I mean, this is just adding up all the graphs below.
The individual factors. Yeah.
Exactly. And I mean, this is exactly, and what you see here, I mean, the higher I go with an electrolyzer stack, the less efficient it gets. That means an electrolyzer I operate at 100% load is less efficient as an electrolyzer I operate at 50% load, or at 20% or 10% and so on. So this is what this graph here shows, right? The more production, the more relative energy I have to put in order to produce 1 kilogram of hydrogen. So by having a thinner membrane, we can get down with the proton ohmic losses in our system. So making the membrane thinner, minimizes or reduces the biggest contribution of losses, especially for high currents. And this allows our system to have overall a higher efficiency.
So cutting the cable shorter, basically, you have less resistance, and that less resistance is just increasing the efficiency.
Exactly, and this is exactly what is happening there. And this, and I mean, this is practically the efficiency increase that we have by using less energy, by reducing the proton ohmic losses because of the thinner membranes, because we can dilute the hydrogen from the hydrogen crossover on the anode side.
Okay. So just getting all that into my head. So that means you can ride this curve sort of at a lower state. Exactly. And I need to ask now, but you need to pump the water in, you need to blow the air in. But that's the same. Is there a big difference?
There is a difference, generally, yes, but I mean, for a classical PEM stack, you need to have some additional components, which we don't need to have. For example, you have an oxygen separation vessel, classically, which we don't have, because we don't have to separate oxygen from hydrogen. We just blow the air and put it to the environment. But therefore, we need to moisten the air, so we have some additional components for the whole system, but also some components less. At the end, it's more or less the same from an effort and volume and cost perspective.
So I'm just getting all this around. So I mean, what you're also doing by blowing extra air inside, and maybe we can just quickly go back to that. Where's that diagram? Does this also cool the system more, or does it make a difference in terms of the thermodynamics?
Yeah, it is a contribution to cooling the system, especially as you are evaporating water there, which also contributes to the cooling of the system on that side. But the main contribution for the cooling is done with the water on this side, as is done. I mean, here's the same. It's actually it's like a big heat exchanger that you're using in order to do that. So. Maybe just one aspect in addition to this higher efficiency. Also a classical PEM stack, you can operate down to usually 20%. Some 15, but this is usually the range until you can go. The reason behind usually is the hydrogen crossover again. Because if I reduce my flow, I have less oxygen, right? Because if I just go from 100 to 20%, I just have 1/5 of the oxygen there. But my hydrogen crossover is not constant, but it's not decreasing as much. So therefore, I have let's assume a constant hydrogen crossover, but only 1/5 of oxygen means I'm having a higher concentration of hydrogen and oxygen. So for this case, in this case here, we don't have this issue as well, because we can just, again, blow more air, even if we go down. And this allows the Hystar stacks to go to as low as 0% or 1% load.
So you can run them at a wider range.
Yes, we can go from really literally 0%, but you just keep like a voltage to the stack, up to 100% up and down. Again, because we are not limited by the hydrogen crossover.
So really, so that means like for your, I don't know, actually not familiar with the operations here, but like solar or wind, they tend to fluctuate. So you would be more accommodating to these kind of fluctuations.
Yes, I mean actually at the end, the limit that we have is more on the system, right? Because you have a hydrogen purification downstream, you have maybe a compressor and so on. So this would be limiting somehow, but not the stack. So with the stack, we can really do whatever we want with this regard.
Okay. So Max, let's see your curve. You've shown us. So thinner membrane is more efficiency. And the safety component is you compensate that by just blowing more air, so you don't need to worry about the thing being thin. What about like wear or like degradation? The famous
big word. No, so we see for ours, so the degradation is not really dependent on the thickness of the membrane. We see a degradation at our systems of around 1.3%, which I think is quite on the average. It's more or less the same. Again, because it's not really dependent on the thickness. So there are other effects contributing to the degradation of your system, which is actually something like you pull in oxygen, and oxygen is building radicals, and then this is eating up your membrane. So this is one of the biggest contributions. This is usually pulled in by water. So in this case here, water is going to the membrane, as we said, is pulling in some oxygen, which will eat up the membrane more or less. In this case here, most of the water is flowing the other direction, right? So we are more or less pushing the oxygen, keeping the oxygen out of the membrane, even contributing to a lower degradation of the overall membrane.
I must say, and this is that, you know, when we were developing fuel cell systems and try to make them safer, we always just said, okay, if there's any problem, just blow more air, you know? So it kind of rings a bell to me that you're just blowing more air. There's air, we have enough anyway, so we just blow it through, and then that's a nice thing.
But this is actually it's a PEM stack which you operate kind of like a fuel cell a little bit, right? So from the idea with the air and so on.
So let's quickly go into the math of it. How can we save money with this now?
So we can save money with this by when we have it in operation, that we just use less energy. And maybe I just brought one snapshot that we have here, which shows our system in real operation.
That's what like the control view would look like.
Okay. So this like exactly a view which you can see. And I mean, I prepared it a little bit here for our purposes, right?
Yes, sir.
But the values that you see are values from real life. So not nice lab values under perfect conditions and so on. No, this is a system operating outside, right? So
running at around 60 degrees, 84% load. 400 kilowatt currently.
Yes, exactly. So we have one stack installed there. So one of our stacks has a maximum operation power of 550 kilowatt. So we are not operating it at 100%, but at 84% only, so 400 kilowatt. This is also why this efficiency is at 45.1. So we guarantee an efficiency of 47.5 kilowatt hours per kilogram. So this wise now is higher, because as we learned before, when you go lower with the load, you have a higher efficiency on your system.
Kilowatt hour per kilogram. Okay, so the less this is smaller, better.
Good. Yes, exactly. Actually, it's not really efficiency. It's the
production basically.
Exactly. Yes.
It's not the efficiency. Exactly. It's not the.
Exactly. So you see it over quite a long time here, where we took these value. You mentioned the temperature. I think this is very important, because it's actually easy to get a high efficiency with nearly every stack, just by putting a very high temperature water through it. So the higher the temperature of the water, the higher the efficiency, or the lower this value. But on the same time, your stack degrades more. So you want to have a low temperature with regards to a low degradation. You want to have a high temperature with regards to a high efficiency. So our system, 60 degrees, is very conservative here that we chose, and we still can show a very high efficiency. By the way, this one here is showing the efficiency on the system, which is, I would not really focus on that, because we have some components of the system which are not considered here. But the stack efficiency is really what we measure in the field.
So you brought this calculation, which I very much see. Can you quickly run us through this?
Yes, of course. No, I mean, we were talking about the efficiency, and at the beginning of our talk, you were talking about how this contributes to overall economics of a system, right? So let's talk about that. So what we did here, I just compared a classical PEM system with a Hystar PEM system, as I call it here. And we just assumed some values from literature, classical energy consumption of a stack at around 54 kilowatt hours per kilogram. Some consumption of the system, which contributes additional 8%, which is also some values from the books. So these are, these values I assumed more or less. And for Hystar, I know the values, obviously. So we guarantee 47.5 kilowatt hours per kilogram.
But that you guarantee that?
Yes, exactly. We guarantee these values. Yes. Not brochure values. It's guaranteed. And then we have a system value of 53.3 kilowatt hours per kilogram. I mentioned before that we get our hydrogen at 5 bar. Actually, usually we combine it with a compressor. And even the compressor energy consumption included, we reach these 53.3 kilowatt hours per kilogram.
Is slightly higher than the 8% you have.
Exactly, because you have a compressor there, but this has already been taken respect of. So to not compare apples with oranges, but to make it all hydrogen at 30 bar. Right?
So what's that, around 12% or so? You have here.
Yes, and then we just assumed an electrolyzer size of 20 megawatts. It also works with bigger or smaller, but for 20 megawatts. And with Hystar, you only need 17.6 megawatt.
So you already need a smaller system.
Yes, exactly, to produce the same amount of hydrogen, because we can just produce more efficiently, right? So you see with this one compared to this one, both systems reach 2,900 tons per year, right? So when you're operating at 8,000 hours, so this is just multiplied here altogether. So then you have your system contribution, and we assumed an electricity cost of 8 cents per kilowatt hour, which I think is for European circumstances, green electricity for these bigger projects, okay-ish in this region. Then we just calculated the annual electricity costs. It's just multiplication of the values is here above, right?
Okay. So in this case, I'm trying to generate about 3,000 tons of hydrogen, and that would cost me annually about nearly 14 million euro.
Exactly.
Yeah.
Yeah.
Okay.
Exactly.
And that's the price of that. Okay.
Yeah.
And here, using this system because it's more efficient.
Yeah.
That would cut the cost to 12.7, something like that.
Exactly.
Okay, there you go. So that means with a 20 megawatt system running a whole year, you're saving over €1 million on that.
Yes, exactly. I mean, for 20 megawatt. I mean, go to 40, it doubles. Go to 10, it goes by half, goes down by half. So, but this is just a reference case here, and I think also most of our viewers will be able to just rebuild this Excel. It's just very straightforward. And I mean, I just want to highlight the importance of efficiency when you're considering your totex of an electrolyzer. It's so much more important than what you pay at the very beginning. You have to look
for the initial setup.
I mean, these systems operate for 20 years, right? And when you're just considering this as an annual saving and then just multiply it by 20, this is at the end you pay so much more for electricity than you pay for the hardware at the very beginning, that this just underlines the importance of this efficiency for your economics of electrolysis projects.
I'm very glad that in this channel we're actually talking about a lot of these technologies that can bring more efficiency to the system, because I think that's very beneficial to the entire hydrogen system. And I mentioned earlier the talk of Aqua Power on that. So Max, this is great, and I hope we can implement more of this so that we can use it more. I know you are from Norway now, and you guys are trying to build the future there. Can you give us just a bit of an outlook of where this is going? Are you still working on getting more efficiency, or just the next?
Yes, of course. I mean, we are currently scaling up. So we are building like a gigafactory, as I think you have to when you're building stacks. Because I mean, it works with the numbering up the amounts of stacks. Actually, our size of the stack, which is 550 kilowatt, we try to limit there. Because we have quite a small stack, and we can make use of lots of fuel cell components for it, which I think is very, very interesting from an economical perspective and also from a production perspective. Of course, we are still also trying to increase the efficiency even more, so we don't stop where we are right now. And we are currently expanding also into Europe and also worldwide, also looking for partnerships there.
Producing, and people can approach you, put these in their system.
Yes, 100%. So especially the stacks. Also, we have a development for a system, for a containerized system.
Yes.
But also especially the stacks, we are open for partnerships in order to get them out in the world, because we want to make the electrolysis industry happen, and therefore you have to make the projects economical. And this is what we think is a good contribution to this.
Okay. Wow. Max, thank you so much. That's a whole lot of it. I totally find this exciting. I'm getting all goosebumps because I mean, this is really where it's coming from. Those things that will make renewables more affordable and better for all of our benefit. Thank you very much, Max, for being here. We hope you liked this video about this kind of stack technology. There's many more to watch. Also, the one of Max with explaining the whole electrolyzer system. If you'd like to give us a like, go on Hyfindr.com, where you can find many more components and things for the hydrogen industry. All the best for you, and have a wonderful day. Thank you, Max.
Thank you so much for having me.